All right, welcome back everybody. We are starting our next unit on waves and optics. And really this unit is going to be mostly focusing on optics, but this first lesson we just kind of need to set some ground rules about waves and how they behave. And of course, optics is going to delve into all about how light behaves, and light is a wave. And so if we know a little bit about waves in general, we will be able to apply that to light. So what in fact is a wave? Well, we could say that a wave is a disturbance that carries energy without displacing matter. Now you could picture like water waves traveling in the ocean and crashing on the beach, and you might think, well, those are moving matter, and they do move matter around, but at the end of the day, after the wave has crashed on the beach and come back down, the matter hasn't really displaced, hasn't gotten anywhere. But what has been transmitted through that water is energy, right? You could imagine a surfer could use that energy to ride along that wave. And so this is true about all waves, whether it's sound or light or waves in a spring or whatever it is that energy gets transmitted without actually carrying or without actually displacing the matter that is moving along with the wave, or that might be moving along with the wave. So if we picture a wave, and this is one example of a wave, there's a few just points, and this might be a bit of a review from last year and other physics courses that you've taken. And so when we have a wave, the kind of the high parts of the wave, we call those the crests of the wave, and the low parts of the wave, the lowest points, we call those the troughs. You can imagine a wave going from crest to trough to crest to trough, repeating over and over again. And so this like center line here, this represents equilibrium. This is what it would look like if there was no wave traveling through this space. Okay, so we call that kind of our equilibrium point. And the distance, like the height of the wave, above that equilibrium point, we call that the amplitude. So the distance from equilibrium up to the highest point is our amplitude, and that's the same as the distance from the equilibrium down to our lowest point. That would also be the amplitude. Now, how far the wave travels, like if I pick a point on the wave here and I go all the way up and all the way down and I complete one cycle back to my starting point, we would call this distance from here to here, that is our wavelength, and we give it the symbol lambda. So that's a wave length. You could think of it as the distance traveled by a single cycle or a single wave. Now, you can't see it on this picture here, but we also got period and frequency. And so period is the time for one cycle. Time for one cycle or one wave or whatever it is. You might remember that from rotational. It's the same idea. And so frequency is related to period, and frequency is the number of cycles per second. Okay, and frequency is measured in hertz. Okay, and so there's a relationship there. If you've got period is the time for one complete cycle, and frequency is the number of cycles per second, then you could say the frequency is just equal to 1 over the period. Okay, so 1 over the time for cycles. All right, now there's a couple of things. We'll just talk really quickly about mechanical waves. This unit isn't really going to cover mechanical waves. It's really going to focus on light. But again, just to kind of set our ground rules. Now, mechanical waves move through a medium. Okay, so a medium is anything that a mechanical wave travels through, which sounds like the same thing I just said. But you could imagine like the sound you're hearing right now is traveling to your eardrum, and it's traveling through air. So air is the medium for the sound wave. You can imagine water waves traveling through a medium of water. And maybe in this like picture of a woman moving a spring around, the medium could be the slinky or the spring. Now, transverse waves, there's two kinds of mechanical waves we'll talk about. There are others, but the two kind of most common kinds we'll talk about are transverse and longitudinal. So for a transverse wave, the medium is going to move perpendicular to the propagation of the wave. Now, what does that mean? You can see there's a transverse wave down here at the bottom. If I had a slinky and I move my hand back and forth like this, you could imagine that if I had like a particle, if I look at one particle on the wave, it's moving up and down, let's say, but the wave itself is propagating this way. So as I oscillate up and down, the wave propagates in the forward direction. So you can see those two are perpendicular to each other. Compare that to a longitudinal wave where the medium moves parallel to propagation. of the wave. So again, in this case, if I pick just like one little particle in this slinky, if you move your hand back and forth like this, you can imagine that one particle is just moving back and forth, but overall the propagation of the wave is in the forwards direction. And so that's our longitudinal. Now, there are lots of examples of each of these. Longitudinal waves, for example, like pressure waves in an earthquake or sound waves and those sorts of things are very interesting. We're going to learn more about transverse waves because as we're going to learn, light travels kind of as a transverse wave. Now, one other thing just to kind of think about before we dive into light and just kind of general theory about waves is that we can think of waves, there's a relationship between waves and periodic motion. So if you learn about rotational motion, then this is going to sound familiar. That I can model, you can imagine this black particle moving around in a circle. I can model its motion in a circle as being like a series of waves. So for example, this blue wave that you see here is really modeling the position of that particle in the x direction. And the red wave is modeling the position of the particle in the y direction. And so we can model these positions or really many properties of the wave, like the frequency and so on, or as we'll see in a second, the strength of the wave. And we can model those using trigonometric functions, okay? So if I just take as an example this blue wave, which is modeling the x position of the particle as a function of time, that would just be x, the x position, is just equal to the amplitude of the wave times the cosine times omega t. Okay, now I've just chosen the x position in this example. I could have done the y position. Some of you might have noticed that the y position looks suspiciously like a sine curve, and so that would be fine. You could talk about sine curves or cosine curves, whichever is sort of more appropriate. But just a reminder about this omega. So this omega is something, again, from kind of rotational or periodic motion, where omega is really the angular velocity, and it is equal to 2 times pi times frequency. Okay, so this is angular velocity. And it just refers to how quickly you're moving around that circle. And you can imagine that that is related to the frequency. And that is measured, by the way, in radians per second. Okay, so 2 pi radians multiplied by hertz is a radian per second. Now, if I substitute this in to that equation I just had, we can see that I could model this as x equals a times the cosine times 2 pi f times t. And again, I could use this to model the position or different properties of the wave. So as an example of that, let's jump over here and take a look at this. I got a radio wave, receives a signal from a radio station broadcasting at a frequency of 830 kilohertz, so 830,000 hertz. The graph below represents the electric field strength of the radio wave at the position of the radio as a function of time. So write the electric field strength E as a function of time based on this graph right here, okay? So, well, a couple things we can just notice from the graph. We know the frequency, right, is 830 hertz. We can kind of take a look at this graph and notice that we're graphing the field strength as a function of time. So I could grab, for example, I could look and find my amplitude. I can see that my amplitude is 1.5. Just be careful of the units here. Times 10 to the negative 4, and the units seem to be volts per meter, which makes sense because we're talking about an electric field strength. I could also, if I needed to, I could pull off of here. I could see this is a measure of time in microseconds, so I could figure out how long it takes to go all the way up and all the way down, all the way back to 0, and that would give me the period. Now, as it happens, I already have the frequency, so I don't need to use the graph to find the period. I could find it with that. And so I'm just going to model my function of time. So the electric field strength as a function of time is going to equal, now in this case, since it starts in this position, I'll model it as a sine curve. It's going to equal a times the sine of 2 pi f times t. And I'm just going to fill in what I know here. So I've got E as a function of t is equal to my amplitude, which is 1.5 times 10 to the negative 4 times the sine of 2 pi times 830,000 times t. And so if we simplify this, we just get that the electric field strength as a function of time is equal to 1.5 times 10 to the negative 4 times the sine of, and this is about 5.6 times 10 to the 6 t. Okay. All right. So let's talk about wave speed. All right. So waves travel at a certain speed, whatever kind of wave it is, and if we look at a single wave, then the distance traveled by the single wave is really just equal to the wavelength. And the time that it takes for a single wave, the time traveled by a single wave, would be equal to the period t. Now, since we know that the speed of anything at a constant velocity is just going to equal d over t, I can substitute into this my wavelength for my distance and my period for my time. And because frequency equals 1 over the period, I end up with the wave equation that just says v equals lambda f. Okay, and again, where v is the speed, lambda is the wavelength, and f is the frequency. All right, and this is going to be true for any wave. But let's talk about electromagnetic radiation, which is really just fancy talk for light. Now, when we think of light, we are thinking about the light that we see, but of course, light comes in a bunch of varieties that we don't get to experience in that way. Now, EM radiation travels as, or we can think of it traveling as, transverse waves of oscillating electric and magnetic fields. Now that's kind of a weird idea, but you can see from this kind of example here. So what I've got as my wave of light travels is it is an oscillating electric field that you can see here in blue, oscillating in one plane, and then perpendicular to that I've got an oscillating magnetic field. And this really comes about from, if you think about Faraday's laws and something called Maxwell's laws and Ampere's law, that essentially if we've got a changing magnetic field, that is going to generate an electric field. And if I have a changing electric field, then that is going to generate a magnetic field. So these waves are essentially disturbances in space that are just causing these ripples in electric and magnetic fields. And they propagate through, lots of things, or nothing, in fact. So the speed of light is really going to depend on the medium. So light can travel through air or water or glass or diamonds or whatever, and the different things that it travels through is going to determine its speed. Now light is special because it can travel in a vacuum. So light does not actually need any medium to travel through. It can travel through essentially nothing. And when it does travel through nothing, through a vacuum, that's the fastest it can travel. So you might have heard that light is like the ultimate speed limit of our universe. And that's true because nothing can travel faster than light in a vacuum. Now the speed of light in a vacuum is so special it gets its own letter c. And it's approximately equal to 3.0 times 10 to the 8 meters per second. So 300 million meters per second, which is very, very fast. But it's not instantaneous, right? And so when we look over larger distances, we notice that actually even light takes time to get there. So as I said, light comes in, electromagnetic radiation comes in a variety of flavors. And what we think about as light is really just this little visible slice here of a whole spectrum. Now, when you look at this spectrum, what you notice as I go from left to right, that I'm starting at radio waves down the far end, and those are low frequency and really, really long wavelength. And then as I travel across all the way to here to gamma rays, I go to shorter wavelength, but really high frequency. Now, keep in mind, all kinds of electromagnetic radiation travel at the same speed. They all travel at the speed of light. But as I change the frequency, what happens is I also change the wavelength. So remember that V equals lambda F. So for example, down at this end of the spectrum, since the speed is constant, I've got a really big wavelength and a small frequency. And over at this end of the spectrum, V equals lambda F, I've got a really small wavelength and a really large frequency. Now, you should probably know these types of electromagnetic radiation, and they're just their approximate position on the spectrum. Okay, so the lowest being radio waves, which we use for radios, obviously, and communicating with things like walkie-talkies and that sort of stuff. And we shift up to microwaves, which we actually use to transmit signals like to cell phones, through cell towers and things like that. And then we get to infrared, and infrared being infra smaller than, and red being red, is just slightly below where we can start to see. And then we get our visible light. And visible light spans all the colors of the rainbow from Roy all the way down to GBIV. And the lowest frequency light, being red light, happens at right around 700 nanometers, and that goes only for about a range of 300 nanometers up to purple or violet light, which clocks in at about 400 nanometers. So we see this one little narrow sort of spectrum. If you keep going further along, well, then we go beyond violet, which gets us to ultraviolet and X-rays and gamma rays. Now, it's important to notice that even though all these things travel at the same speed, of course, they do have very different energies, whereas radio waves have lower energy, and then gamma rays have very, very high, dangerously high energy. That's because they're at a higher frequency. So they travel at the same speed, but the higher the frequency, the higher the energy, and those two are related. So let's just do a couple of quick calculations. Alpha Centauri is the nearest solar system to ours, and it's only just a few kilometers away. So how long does it take for light to travel from Alpha Centauri to us when we look up in the night sky? So we know that V equals d over t, and I can use this formula for waves because waves tend to travel at a constant speed, although we'll see in a later video that's not always true. So the time that it takes is going to be the distance it has to travel divided by the speed. Now the distance is 4.07. Be careful here, it's times 10 to the 16 because this is in kilometers, so I need 1,000 times more to get into meters. And I'm going to divide that by the speed of light, which is 3.0 times 10 to the 8 meters per second. Now this time works out to be about 1.36 times 10 to the 8 seconds, which is kind of hard to picture in seconds, but if you work out the math, that's about 4.3 years, which is to say that Alpha Centauri is 4.3 light years away, that if we wanted to send a message there, it would take light, the fastest thing in our universe, still over 4 years just to get there. Okay, so next question. We've got a laser pointer emits red light with a wavelength of 670 nanometers. What's the frequency of the laser? So in this case, I can use V equals lambda F because they're asking about the frequency. So frequency is just going to equal the speed divided by the wavelength. Now the speed is 3 times 10 to the 8 meters per second. And then the wavelength is 670 nanometers. So that's 670 times 10 to the negative 9. Remember, nano is negative 9. And so the frequency ends up being 4.5 times 10 to the 14 hertz. So it's good to just kind of keep in mind just approximate frequencies and wavelengths. The wavelengths of light we see are in the nanometer range. The frequency of those wavelengths are then very very high, 10 to the 14 hertz, just as an example. All right, so let's just talk one last thing before we finish up, and that is polarization. So this is kind of a neat feature of light. So we know that light travels as a transverse wave. Okay, now normal light is unpolarized, and what we mean by that is that it is traveling not just in one plane. So it's a transverse wave. You might think of that as going up and down, but like you can see here from this little graphic, that it could be going up and down, or it could be kind of going in and out of the page, or it could be going at some angle in between. So unpolarized light is traveling in all different planes all the time. It's going this way and this way and this way and everything in between. So it travels in all planes. Now, polarization is basically the process of forcing light to travel in a single plane. So the process of forcing light to travel in a single plane. Now, what do we mean by that? Well, kind of the analogy we often use is thinking about like some fence posts, okay? So if light is traveling in all these different planes, you can see this polarizer that I set up in the middle of the graphic, that all those different planes come along, and there's basically a fence post. And the fence posts have gaps in them in very regular kind of locations, all say horizontal. Well, light that happens to be traveling in that horizontal plane is just going to go straight on through as though nothing happened. But light that's traveling at an angle that maybe it's trying to travel this way is not going to be able to pass through the polarizer. And so that light will not be transmitted. And light that's kind of in between might be partially transmitted. So essentially, any light that makes it through this polarizer is only going to be traveling in a single plane. We call it a polarization filter. Now, a great example of that would be like sunglasses, right? When you have glare, when light hits snow or water, when it reflects off, it's really hard to look at. And that's not just because it's bright, it's because it's very, very, very unpolarized. And it's just hard for your eyes to take in that information. When you put on sunglasses that are polarized, it takes that light and it filters some of it out, so it's less bright, but it also only allows in the light that is polarized. And so it's easier for your eyes to kind of deal with the information that's coming at it. Okay, that is it for our first lesson on optics.